Hello, everyone. How are you guys doing today? It's so nice to see you guys again after a long time. I feel like I didn't see you for a while, right? We didn't have any class Monday, and then we had Wednesday, and then we had our exam. So yeah, it's been a long time. So we have one more online class this Wednesday, and then we have a break after next Monday, and then we're going to have all in-person classes. We have only 10 more days once we come back from our vacation. Okay. And I also posted grades on Brightspace. Did you see your grades? Yeah. Surprisingly, a few of you failed, which actually never happened before. In my matrix algebra, everybody always passed. I mean, not everybody. Probably one didn't pass, but except for one, always everybody passed. But this time, 5 or 6 failed. Wow, it's a lot. So I'm going to return your exam at the end of the class today. And I would like to tell you something that calculator is only for calculation, okay? It doesn't replace your work. So if you did all the work mentally using calculator and just give me the final answer, how do you expect to get full credit? Okay, so if you did that, I wrote a comment on your exam. Please do not do that in future. This was the first time, so I was nice. I graded very nicely. I gave you points for at least something because I didn't warn you before. But from next exams, the second exam and the final exam, if you do not show correct work details, then you're not going to get any credit at all. Even though the answers are correct, I'm not going to accept the answer. Okay? So you may copy from your neighbors and tell me, oh, I use calculator. How would I know? I want to see your brain. Did you really learn the materials or not? Do you really deserve the points or not? Okay. So that's why please make sure always show the work. Even though you know everything in your head, it's okay. I don't know that you know. So show me you know, so I can give you rewards for knowing the materials you're supposed to know. Okay. Same thing also in the homework. If you just give me answer, skip all the steps and tell me R1 is R3 plus 5 half R7. Well, did you do 5 half R7 in your head and then add or subtract the other one? Like, come on, show me the work. Just because I said, make sure to state all the operation, all the raw operation you do, it doesn't mean only give me the raw operation and then skip all the work. Show me the work. Even if you use a calculator, whatever you punch in the calculator, tell me the answer. What did you get from the calculator once you do the raw operation? So please do not do that in your homework and also in the exam. And we are done in chapter 1, 2. We are starting chapter 3 today. We have chapter 3, chapter 4 full, and then only one section in 5, one section in 6. So we have probably 4, 4, 8, 9 or 10 sections. And our second exam, I am not sure about the date yet, but we will have a vacation on April 1st to April 9th. And then I'm planning to give you our second exam on end of April. So which day we are going to decide later. On which materials we are going to decide later. For now, it's only, just know that it will be end of, not October, sorry, end of April. Okay. Any question, comment, concern?
I have issues with my white space. I'm pretty sure.
Yeah, they just told me that today is not working.
That. So, submission.
You have till Wednesday.
Oh, it
says due is today, but it will still be visible till Wednesday.
Okay.
So you have still time till Wednesday, if I'm not wrong, right? I always give 2 days extra, just in case you cannot make it the deadline. You have to make the second deadline. And also I decided to post a solution once that due date is over for homework. So from now on, I'll try to post the solution so you can see the correct method of solving them. Okay, chapter 3. Chapter 3, we are going to do completely different than what we did in chapter 1 and 2. And from here, our hard life starts. Okay? So chapter 1 and 2 was fun. It was easy to understandable, everything. But chapter 3, it's really hard to explain with words. So in chapter 3, we are going to watch lots of videos every day. Not every day, like before I introduce to any not hard, like whatever I cannot explain that cannot be visualized with words, I'm going to show you videos on those topics so you can visualize all the things we're going to discuss in class. We start with vector space. So vector space there are several types of vector space. A vector space is full of vectors, okay? And you all know what is vector, right? Vector, how do I explain what is a vector? Vector is an array that starts from the origin and goes to any direction on the plane. Like in R2, if you are in R2 space, it means XY plane, then if it starts from the origin and go here, this is a vector. Or if you start from the origin, go this direction, this is a vector. Or this is a vector, or this is a vector. So usually the vector starts from the origin and it has a direction and it has a length. So vector has two things. The direction means which direction you're moving. Is it going to positive direction or negative direction? And how much is the length of the vector? So every vector consists of two things, direction and the length. And with these vectors, we have several types of vector space. We are going to discuss Euclidean vector space in this class. So what is Euclidean vector space? Euclidean vector spaces consist of vectors which are mathematical objects that have both magnitude and direction. Magnitude means length, and direction, you know what is that, like which direction it's going. Vectors are represented as directed line segment with an arrow in R2 or in R3 and are used to model physical quantities like displacements, velocity, force, electromagnetic fields, etc. So we are going to discuss R2 and R3 in this class, but besides these two, we actually have higher dimensional vector spaces, which if you take the real linear algebra, you're going to learn those in real linear algebra. So what do we do in R2 or in R3? What type of operations are allowed? If we have two vectors, let's say U and V, they consist of two elements, X and Y. So whatever we have here, we have an X value and we have a Y value. So if you just look at the point, we write XY as a point format. But if you look at the point using a direction and magnitude, then it becomes a vector. And every vector we write as a column matrix. So we write X and Y in a square long bracket. So if you see only parentheses, it means it's a point. But if you see a square bracket and then they're written as a column, then it's a vector, not a point. Now, if you have a vector U that has X value E1, Y value E2, and you have another vector V that has X value V1, Y value V2, then with these two vectors, we can do so many things. We can add them. In order to add the two vectors, we add their X values and we add their Y values. Whatever we get, that will give us a new vector, which is the sum of these two vectors. Also, we can subtract them and we can multiply each vector by a non-zero scalar. So non-zero scalar, when you multiply both X value and Y value individually. That will give you a new point. So if you draw an arrow from origin to that new point, it will give you the new matrix or the new vector. which is the constant multiplication of a vector. And we can say two vectors, they're equal if and only if both elements are equal to each other. So U and V, they will be equal if the X value in U and X value in V are the same number, and also Y value in U and Y value in V are the same number. So two vectors are same exactly if the X's are same and their Y's are same. Negative vectors means it's going on the negative direction. So positive direction is always going this way or this way. Negative means you're moving in the Y direction negatively. So negative, negative. These are negative. Sorry, definitely this is negative and this is positive. Let me erase the other two. These two will be a combination of the positive and negative. The original positive goes on the first quadrant. The original negative goes on the second, the third quadrant. And then the second and the fourth, these are the combination of the other two. Okay. Now, we also have a very important concept in a vector. It's called norm, which is the length or magnitude. Now, depending on what type of field you are in, we take the length of your vector differently. But this norm, vector norm, is a measure of the magnitude of a vector. Means how much is the length from 0 to the tip of your point, tip of your vector. So in other words, norm measures the size or the length of a vector. And we have different norms that measures different ways. For example, in our real life, we have centimeter, meter, inches. We have so many different units to measure the same thing. So same thing to measure the norm, the same length, we have different ways of measuring them. The first one is called L1 norm or Manhattan distance. In this norm, we take the sum of the absolute value of each element. So if you have a vector with multiple elements, to get its length of how much is the distance from the origin to the tip of your vector, all you have to do is add all the elements. Even if you have a negative sign, ignore the negative sign. So in other words, basically add their absolute value. For example, if you have a vector 2, 3. So if you want to draw the vector 2, 3, 2 is here, 3 is here. So this is our vector from the origin 2, 3. So if you want to know how much is the distance from the origin to the tip of the point 2, 3, you take their x distance plus their y distance. So you walk this direction and you get the result 2 plus 3, 5 units. You're just walking not straight, you're walking differently. You're walking in the x direction and the y direction. This is L1 norm or the Manhattan norm. In this distance, we use this type of distance when we do optimization or statistic. Then there is another way of finding our norm, which is the main concept in our class, Euclidean norm. In Euclidean norm, we take the straight distance between 2 points. So we want to see, so let me actually highlight. Here we take the x distance and the y distance. And in Euclidean norm, we don't want to walk far. So 2, 3, we want to walk straight from the origin to the tip of the point. And we all know in order to get the straight distance between 2 points, we need to use the distance formula. And here we use the distance formula by taking the square of each quantity. So we take square of the x and square of the y and take the square root of their sum. So it's basically we are using a square plus b square equals c square. If you want to get the c, which is the direct distance from the origin to the tip, then you have to do x squared plus y squared and take the square root. So c squared equals a squared plus b squared. That means c is square root of a squared plus b squared. For example, here we have 2 squared plus 3 squared. So 4 plus 9, that gives us 13, and then take the square root. So that's direct distance between the origin 0, 0 and the tip of your point, which is 2, negative 3, is square root of 13 units, if you try to go straight. And it's a straight line distance. We use it to measure, use it in geometry to find distance in the Pythagorean theorem. And anytime you see the word find the norm of a vector, by default, it means take the Euclidean norm or L2 norm. Okay. Anytime they do not mention specifically take L1 norm or other norm, if only they say find the norm of this vector or find the magnitude of this vector, it means you have to use this method, the Euclidean norm. Then we have the last one in this class, infinity norm. Infinity norm has 2 other names. One is maximum norm and the other one is Chebyshev norm. I didn't write it here. But how do you find the norm here? We take the maximum of the value, maximum of the x or maximum of the y. So again, we have 2 here, 3 here, 2, negative 3. In this method, we just take what's the highest distance from x units and the y units. So here we have highest distance, the y. So our distance is 3 units. We are measuring the same thing, the norm, the length of the vector, but we are using different methods. Like how to use centimeter versus meter versus inches. We are doing the same thing, but different units. So here, same thing, same measurement, same length, but different measurements. We used this infinity norm or maximum norm to find approximation or error bound, like maximum error, largest deviation, and it represents the maximum magnitude among all the components. So basically it measures the worst case size or the largest deviation we can have. In other words, L1 is the total distance from your origin to the tip of your vector. L2 norm is the straight distance between origin and the tip of your vector. And infinity norm is the maximum distance we can have on any direction from the origin to the tip of your vector. So this is the tip of the vector. Anytime I say tip of the vector, I mean here, this point. So that's how we do it in R2 space. Now, let's say you have a matrix. Instead of one vector, you have a matrix vector. It means we have a lot of vectors in one matrix. So to find the matrix norm, then we use the same concept, but we use differently. For L1 norm, we take the maximum absolute sum column-wise. So if you have a matrix with lots of columns, we see which column has the largest, the highest sum. Our norm is that number. For L2, it's same. We take the square of each quantity in the entire matrix, and we take their sum and the square root of the sum. For infinity norm, we do the same thing as L1 norm, but this time we take the maximum sum row-wise. We add all the rows and see which rows has the maximum sum. Our length is, our norm or the length is that maximum number row-wise. So for R2, it's simple. for R3, we have to keep doing sum for everything. Eric.
I still don't really understand the difference between L1 and L2.
L1, it's total distance. How much is the total distance from one point to another point? Infinity is what's the maximum distance. If you go this way and this way and this way, among all the direction you're moving, which distance is the highest distance? That's the maximum distance in every direction.
So is it the maximum between the L1 and L2?
No, L1 is the total distance. So if you walk, let's say from here to here, you are walking this way and then this way, right? So the total of this plus that is L1. But what is infinity? Infinity says measure from here to here and here to here. Whichever is the highest, that's your infinity norm. Means maximum norm. So in this example, this is our highest in the x direction. So our infinity norm is that much. L1 is the total, but infinity is maximum. So matrix wise, I have three matrices here, 2 by 2, 3 by 3. So in the first one, if you want to find L1 norm, you look at them column wise. You look at the sum of this and sum of this. Their absolute value, okay? All the elements absolute value. If you add 2 plus 3, we get 5. And if you get 8 plus 1, we get 9. We have maximum 9. So L1 norm for this one, L1 is 9. Because we are in a matrix field. If you're in the matrix field, we look at them column wise. Whichever has the highest sum, whichever column is the highest sum with the absolute value element, then the distance is that one, the highest one. Column wise for L1. But if you want to take L infinity, you look at them row wise. Row wise, we have 8 plus 10, with 8 plus 2, 10, and 3 plus 1, 4. So for infinity norm, our answer is 10. If you look at L1 wise, it's 9 units. If you look at infinity wise, it's 10 units. So infinity takes the sum of the row and 1 take sum of the column. On the other hand, the L2 or the Euclidean, it takes everything. It doesn't matter if you look at row wise or column wise, doesn't matter. You have to take every element and square them. So for L2, we have 2 squared 4, 8 squared 16, 3 squared 9, 1 squared 1. You add all of these, whatever you get, that's your L2 norm or the Euclidean norm. So we use Euclidean norm often because it considers everything. It doesn't discriminate anything. Where L1 only look at column, infinity look at only row. So they discriminate the other one. But L2 is the fair one, the most fair one. It takes everything. It's like a fair ruler, a fair king. Okay. Similarly, if you look at B, if you want to find L1, if you want to find L1 for B, you add all of these, you get 3 plus 3, 6, 8. Sum of these is 10, 11. Sum of these is 7 and 8, 7 and 1, 8. So L1 is the highest one, 11. If you want to look at infinity norm, you add this way. 3 plus 6 is 9, plus 1, 10. 3 plus 1 is 4. 7, 8, 9, 7, 11, 13. So if you look at infinity norm, our infinity norm is 13 units. And lastly, if you want to take the fair norm, you take square of every unit. I don't have it here, but it's 3 square plus 6 square plus 1 square plus da 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 da. Whatever you get, that's your L2 norm. Any question? So in this example, they use the 3 example for 3 different types of norm. The first one is for L1, the second one they use for infinity, and the third one they use for L2. But for the same matrix, you can find all 3 types of norm. It's the same measurement length, but you just look at different way. Any questions so far? Go ahead. You just need to have an idea how much is the length. So you can have one decimal space, 2 or 3. It's also fine. As long as you have an idea how much is the square root of 89. Okay, now comes the actual exam question. If I have space, then I'm going to give those questions. Like, those are easy questions. You don't have to do hard math. So these are if exam, if have space. Exam, if I have space. Now, what I want to really put in the exam is the next one. Consider you have 2 vectors, 8, 6, and 4, -1. So like I said, if you write them as a point-wise, it means it's a point. So anytime you use parentheses and you write them row-wise, you have to use a T. T means transpose. Because normally every vector is written as a column vector. We never write them as a row vector, normally. So let's say you don't have space to write them as a column vector. So you have to write a row vector, no problem. Write the row vector, but make sure to put T so that people can understand it's a column vector 8, 6, not a point 8, 6. So we have 2 vectors, x1, 8, 6, and x2, 4, -1. And it says find the length of each vector. And they didn't mention which length. So if they never mention which length is supposed to find? L2. That's the normal length. The normal, by default, it's our normal length. So we want to find, and norm we represent by 2 absolute value bar. So if you want to find norm of x1, it means double absolute value of x1. So how do you find it? L2 norm, how do you find L2 norm? They're squares. So square root of every element you see, they're squares. Square root of sum of every element square. So what is 8 square? And 6 square? If you add them, how much we get? Square root of 100 gives 10. So the distance between these two, sorry, not these two, the distance between the here and 8 and 6, the distance between, the direct distance between 8, 6 and 0, 0 is 10 units. So this is 8, 6. Now we also have to find the norm of x2. So what's the norm of x2? How do you find it? 4 square plus 1 square. So we get 16 plus 1, 17. And how much is approximately square root of 17? It's between which two numbers? 4 and 5. Because square root of 16 is 4, square root of 25 is 5, and 17 is between them. So it's definitely between 4 and 5. So it's 4 point something. If you don't have a calculator, that's how you can approximate. 4.1, I don't know, but we know it's 4 point something. Now, why do we care? We care because we have to compare them in B. B says, do something new. Add x1 and x2. And that will give you a new vector x3. So x3 is x1 plus x2. That means we are adding vector 8, 6 and vector 4, -1. And do you remember how do you add vectors? It's a matrix. How do you add matrices? So 6 minus 1 is 5, 8 plus 4 is 12. So we add them element-wise. You add these two, you add these two, and you get the new matrix. And then it says, find the length of this x3. So we have to find the norm of x3. Bless you. So what's the norm of x3? Eric.
12 squared plus 5 squared for root of that.
12 square and 5 square. So how much you get?
44 plus 25.
Mm-hmm.
And that's equal to square root of 169. And that's equal to 30.
That's a good number, a whole number 13. So we found x3 has length 13, x1 is 10, and x2 is 4 point something. Now it says, how does its length compare with the sum of the length of x1 and x2? So norm of x1 was 10. Norm of x2 was 4 point something. It says if you add them, then what do you get? Norm of x1 plus norm of x2 is 10 plus 4 point something, which is 14 point something. So if you compare this sum with x3 is 13. What do you observe? Which one is larger? The sum of the norm or the sum of the norm of the sum? Okay. Sum of the norm is this. You are adding the two norms. And then sum of the vector, the norm of the sum of the vector. So which one is higher? Sum of the norm or the sum of the vectors? It's talking about sum, right? They're adding two things. We're adding the vectors here and get the sum, get the norm. Is this bigger? Or if you add the two norm, this is bigger. Sum of the norms. And this is sum of the vectors. Which one is higher? Sum of the norms. So you can add the vectors and get the sum, but that sum will always be lower than if you add the individual norm for each vector. In other words, if you have x1 x1 plus x2 norm, and if you compare that with x1 plus x2 norm, which type of inequality is supposed to put? This way or that way? It should be this way, right? Because the sum is bigger. When you add x1 and x2, we get 14. But when we add the vectors and then get the norm, it's lower. So this one has a special name, I forgot. It's a special property. And it has a special name. If you take real linear algebra, you're going to work with that. Triangle inequality? Something like that, I forgot what it's name. So maybe in the exam, I'll ask this as multiple choice. If you add the sum, how does it compare with the sum of the norm? Okay. Okay, now we have vector space with some important properties. So a vector space is a set of objects called vectors that can be added together and multiplied by a number, a non-zero scalar, in a way that satisfies a specific set of rules called axioms. These operations must be well defined, meaning the addition results in another vector within the vector space. And when you multiply by a scalar, that have to be within the vector space. So what's the title for the first one? Euclidean vector spaces. Okay. Now, there's an example. If V is a vector space, then vector addition takes two vectors in V and produces their sum in V. And scalar multiplication takes a vector, non-zero scalar, and takes a vector, multiply them, the result has to be in V. What does it mean? In other words, not every space can be a vector space. In order to be a vector space, there are two conditions you must satisfy. Which two conditions? We call them vector addition and scalar multiplication. So let's say you have a vector space. If you take any two vectors, let's say one vector is here, another vector is here. If you take any two vectors from this vector space and add them, so let's say this is V1 and this is V2. If you add them, then this V1 plus this V2 going to produce a new vector. This vector has to be inside your vector space. It cannot go outside. If it goes outside, then it's not a vector space. So this is one condition. Take any two vectors from a vector space, add them, the sum has to be inside your vector space. The second condition says, take any vector and a scalar multiplication, and a scalar number, any non-zero number. So let's say I took 3. So if you multiply 3 with your vector, then you're going to get a new vector. That new vector also has to be inside your vector space. If it doesn't, then it's not a vector space. And it's true, it has to be true for any number. Take any number, multiply the vector by that number, any non-zero number. The result has to be in your space. Take any two vectors, add them, the sum has to be inside the space. If these two conditions fulfilled, only then the space you're working with is a vector space. So we have lots of spaces, okay? There's so many spaces. Not every space is a vector space. That's the main concept here. One example, which is not a vector space. Let's say we take a space. In this space, our first element could be anything, but the second element must be 1. Okay? Take any first element. So basically, x value could be anything, but your y value has to be 1, definitely. So if you look at in 2D plane, this is an example where you have y equals 1 line. X could be anything, -1, +1, -2, +2, anything, but your Y value always has to be 1. And suppose this is a space, you want to test whether this is a vector space or not. If you take a horizontal line, does it represent a vector space? Or is it a vector space itself? So in order to see whether this is a vector space or not, you take any two vectors here. So let's say you took one vector 3, 1 and another vector 5, 1. Okay. See, this condition fulfilled, our Y value is always 1 and we have different X values. So you take two vectors, one is 3, 1, the other vector is 5, 1. And if you add them, what do you get? 3 plus 5 gives us 8. And 1 plus 1 gives us 2. Now, if you look at the vector 8, 2, does it have the same characteristic as our original space? The original space says your Y value always has to be 1. This is the set we took. Y value is 1. But when you added the two vectors in your space, what's the Y value you got? 2. So does it have the same characteristic as our set? No. So it's not a vector space. So this is just a set, but this set is not a vector space. It doesn't represent a vector space. So it failed the addition. We have to check both of them. If you have to check both of them if it's true, but if one of them is failed, one of them is false, then you don't have to check both. It's automatically false. So what we do in this chapter is that we take a bunch of sets, different types of sets, and we test, does each set represent a vector space or not? So basically we are testing if we take two vectors from this set, add them, do you have the same characteristic as the original set? If you don't, then it's not a vector space. But if you do, then we check the second condition. We multiply our sets, take one vector, multiply by a constant, and if the results have the same characteristic as our set, then it's true, otherwise it's false. Let's do a few examples. Oh, before that, let me introduce you to some axioms. It says a set V together with operations of addition and scalar multiplication is said to form a vector space if the following axioms are satisfied. So the sum of xy is same as sum of yx. It means it doesn't matter how you add them. You can add them from left to right, or you can add them from right to left. You have the same result. If you add three vectors, it doesn't matter your operation. You can add first two and then add the third, or you can add second and third and then add the first. It doesn't matter. There exists a zero element in the vector space. So when we add the zero element with the vector, it doesn't change anything in the vector. So just like normal number, any number plus 0 is the same number. So any vector plus 0 vector is the same vector. For every x in your vector, there exists a negative x. So if you add x with negative x, you end up getting the 0 vector. Just like the number. If you add 2 with negative 2, the result is 0. Same thing, if you take a positive vector with its negative vector, add these two, the result has to be 0 vector. If you multiply by a scalar with the sum of two vectors, you can multiply each vector with the scalar and then add the product. It's like distribution property. Or if you add two scalars and then want to multiply by a vector, you can multiply each scalar by the vector and then add the sum. Another distribution. Same thing for multiplication, the order doesn't matter. You can multiply the constant and then multiply the vector. Or you can multiply one vector with the constant, so vector with one constant, and then multiply the result with the other vector, other constant. In other words, the multiplication order doesn't matter. And lastly, 1 times any vector is the vector itself. And all the results we talked about all these things have to be inside your vector space. If one of them goes outside the vector space, then the space you are working with, it's not a vector space. So all these sum add up to these two conditions. So whatever we have there, the two conditions summarize all these things we're supposed to have. So that's why anytime you test whether a set is a vector space or not, we can only check the scalar multiplication and vector addition. Now, there are a few important types of vector space we're going to work in this class. I mean, not in this class, in real life. We have continuous real valued function vector space, and we have polynomial vector space. Also, we have matrix vector space and complex number vector space. So you have so many types of vector space. But in this class, main thing will be matrix, I think. And with this, we're done with section 3.1. So 3.1 introduces you to vector space. What is a vector space? How do you know something is a vector space or not? So there is no homework for 3.1. Because all the questions they have are theoretical questions. Prove this is a vector space. Prove this is that, this is that. And those are not so much application we have there. Now, 3.2 is a continuous part of 3.1. In 3.1, we learn what is a vector space. And in 3.2, we are going to learn what is a subspace. It means if you do have a vector space, you take a small part and you want to see the small part you took, is it a subspace of your bigger vector space? It means we have to show whatever characteristic the bigger vector space have. If those characteristics we have inside the small space, then it's a subspace. So whatever we have in the bigger space, if you have the same characteristic in the small space, then it's a subspace. Otherwise, it's not. That's the main idea. So given a vector space V, it is often possible to form another vector space by taking a subset S of your vector space V and using the operations of V. Since V is a vector space, the operations of addition and scalar multiplication always produce another vector in V. For a new system using subset S of V as its universal set to a vector space, the set S must be closed under the operation of addition and scalar multiplication. That is, the sum of two elements in S must be in the S, and the product of the scalar and the product of the scalar and vector must be in S. In other words, the two characteristics we discussed in vector space, the sum of vectors must be in the vector. So same thing has to be for the subspace. You take two vectors from the subspace, add them, the result must be in the subspace. And if you multiply the vector in the subspace with the scalar multiplication, then their product has to be inside your subspace. Then the space you took is a subspace of the original vector space. Let's see. Yeah, it's only 5 minutes, you have enough time. So let's watch here. Hold on, let me make it louder.
we understand what makes up a vector space, it is fairly easy to understand the concept of subspaces as well. To put it simply, a subspace is a smaller set within a vector space that is itself a vector space. Let's look at some examples to clarify. Let's say that V is a vector space. Now we can highlight this smaller section of V and call it S. Every element of S was already also in our vector space V, so we know they all obey the properties we discussed in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space, and because it is completely contained in the larger vector space V, we will then call it a subspace of V. We saw last time that R3, or the set of all real vectors of length 3, was a vector space. So now let's look at a specific choice of vectors contained within R3 and see if it makes up its own vector space, thus qualifying as a subspace of R3. For this example, we will choose a set S made of vectors that have the form x, 0, negative x. By limiting the form of the vector like this, we have chosen a smaller set of R3, while knowing that our chosen set of vectors still follows the rules of the larger set. What we must check now is if our smaller set is closed by checking the two properties of closure. First, let's multiply a vector x by a scalar c. Distributing the scalar c, we end up with a vector cx0, negative cx. Notice that this still has the same form that we want for our set, with some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is therefore still in our set S. Next, let's take two vectors, x and y, both from the set S, and add them together. Provided that we factor the negative sign out of this sum, we will see that the third entry is simply the negative version of the first. And once again, we find a result in the same form as we started. This means that the sum is also contained in our set S. We have verified that S is closed, making it a vector space. And because it was contained within the larger vector space V, this makes S a subspace of V. Before going further, it's important to introduce a few more concepts. Once again, let's say we have a vector space V and a number of elements of V, which we can call V1, V2, all the way to Vn. Any sum of these elements multiplied by some scalars, which we can represent as A1, V1 plus A2, V2, and so on, up to An, Vn, is called a linear combination. The set of all possible linear combinations of these elements is called their span. As an example, let's take three vectors from R3, those being 2, 1, negative 1, 0, 2, 2, and negative 1, negative 1, negative 1. The span of these three vectors will be given by the linear combination AV1 plus BV2 plus CV3, where A, B, and C are all scalars. Let's plug in our vectors and distribute the scalars, and then do vector addition to see that the span of these three vectors has the form 2A minus C, A plus 2B minus C, negative A plus 2B minus C. It's worth noting that the span of any number of elements of a vector space V is also a subspace of V. In fact, it is the smallest subspace of V that contains that set of elements, as it is the intersection of all subspaces that contain them. Span will end up playing a significant role when it comes to completely describing vector spaces. But for now, let's check comprehension.
So that's the main idea of 3.2. We have to check by taking a subset of a vector space and see whether the set we took, does it represent the vector space or not. So let me skip all these things and let's do some examples. The first example says, let's say we have a set in R2 and the characteristic of this set is that when you add the two elements x value and y value, the result is always 0. Okay, so you took a set from R2. R2 is a vector space. R2 means xy plane. So if you take your entire xy plane and you took only a subset that has a characteristic, when you add x and y, the result is 0. Now that subset, is it a vector space or not? It's definitely a subset of your xy plane. But is it a vector space? If it's a vector space, then it's a subspace. Now to check, we have to check two conditions plus one more here. So previously we looked at vector addition. So when it says it's closed under vector addition, it means when you add two vectors, the sum has to be in the vector. And when it says closed under scalar multiplication, it means you multiply the vector with a number, the result has to be in the vector. So we used these two previously, and when you work with subspace, it needs one more condition. The 0 vector must be inside your space. So do you have 0 in your space? Do you have addition satisfied in your space? Do you have multiplication, scalar multiplication satisfied in your space? If you have these three conditions satisfied, then yes, that's the set you took is a vector space of the bigger set. So a bigger set is R2, is definitely a vector space. We took a smaller set where the sum of the x and y value is 0. Now to check whether the sum of the set that has x and y value, the sum of x and y is 0, whether it's a subspace of R2 or not, we first have to check whether we have 0 inside our set. It means we take 0 from the set and we apply the characteristic in the 0 and see what do you get. So if you take 0, your x value, x1 is 0, your x2 is 0, and if you add them, x1 plus x2, you get 0. So 0 is inside our set. That's how we take 0. We replace all the variables with 0 and see what's the sum. The second condition says take any two vectors from your space, from your subset, add them and see if it has the same characteristic as your original set. So let's say we took two vectors. One is U and one is V. So U is U1, U2, and V is V1, V2. And they are in S. It means since our U is in the set, that means if we add U1 and U2, the result must be 0. Because you took it from the set. So every vector you took from the set, it has to have the same characteristic as your set. We took another vector V from the set. It means if we add the two components V1 and V2, the result has to be 0. Because this is the characteristic of the set. Add the two components in your vector, the result must be 0. So now if you add this U and V, that means you're adding these four things, U1 plus U2 plus V1 plus V2. So all of these, when you add, you can rearrange them. So let me actually do it here. U plus V means U1, U2 plus V1, V2. And we know that sum, we always add vectors component-wise. So our sum is U1 plus V1, U2 plus V2. This is our sum. Now, if you look at some in row wise, so you get U1 and U2, you can put them together. V1 and V2, you can put them together. But we know E1, U2 is 0 because this is the vector we got from the S. And you also know V1 and V2 is 0 because this is the vector we got from S. So their sum of the two components has to be 0. So you are adding basically two zeros, the result is 0. So you found that if you take any two vectors from the set, add them, the results satisfy the same condition as the original one. So it's our vector space. It's in our vector space. So we checked the first condition. We checked the second condition. And now the last condition is scalar multiplication. You take only one vector from the space. So if you take, let's say, V, that means V1 plus V2 will be 0 because this is the characteristic of our set. So if you multiply by a constant, you get CV1, CV2. And then if you take C as a common factor, you get C times V1, V2. But we know V1, V2 is 0 because this is the characteristic of the set. So you get C times 0, which is 0. In other words, if you take a vector from the set, multiply by a constant, the result is 0. So 0 vector is inside the set. The sum of two vectors is 0, which is inside the set. Multiplication of a scalar and the vector is 0, which is inside the set. So all three conditions satisfied means all three characteristics give us the same original characteristic from the set. So yes, this is a subspace of our R2. But not every subspace will be a vector space. Or not, sorry, not every subset will be a subspace. We can take subset, but you have to realize whether the set we have is a subspace or not. We need to check these three conditions. And in the exam, you are going to check this. It doesn't work. But it's okay. I'm going to return your exam. But before that, let me take the attendance real quick. Ahmed, absent. Christel, Christian, Danielle, Eric, Florence, Franklin, Gassan, absent. Halil, absent. Imran, Jackie, Jerry, Jonathan, Juan, absent. Julian, Karma, Kate, Kathy, Man, Matthew, Melissa, Mohammed, Monatha, Omar C, Omar D, absent. Prabod, absent. Rahmanjan, Rayat, Sadia Sattar, Sadia Sheikh, absent. Sam, Samuel, absent. Saraya, Saima, Stephanie, absent. Valerie, I'm going to put the solution of the exam later, so you can check your work with the solution. And let me know if you have any complaint. Man. Absent. Jackie, Karima, Crystal, Florence, Rahmanjan, Julian. I forgot to put the number, it's 100. Valerie, Jonathan, Prabal, Mohammed, Jerry, Karma, Franklin, Kathy, Omar C, Stephanie, Sadia, Daniel, Saraya, one absent. Khalil absent. Matthew, Samuel, Kate, Christian, Eric, Imran, Raya, check whether you have one exam or two exams. Because all the staples are weird here. Okay, so in question 1C, a few of you wrote infinite solution and then you stopped. But I told you the entire semester before the exam, even for infinite solution, you have to write x equals, y equals, z equals in terms of free variable. And if you just write, if z is the free variable, you wrote x equals this, y equals this, and did not mention what is your free variable, I took off points. So you have to indicate exactly what it says. Question 4. A lot of you have no idea what is matrix equation Ax equals B. You simply gave me A is this, X is this, B is this. I did not give you any credit because you did not write the matrix equation. In matrix equation, you write A times your X variable matrix equals your V matrix. You have to write as a matrix equation. I took off points for question 5 for almost all of you. Almost. Because even though I said many times in class, but you forgot. AX is same as not XA. In matrix multiplication, the order does matter. So if you write C minus A times X, and you write X times C minus A, definitely they are not same. So if you got the order wrong, I took off points. I was very nice in question 6, even though you did not get any of the variable correct, but I still gave you 1 point just for trying hard. Okay. So A has a unique solution. B doesn't have a unique solution. B has infinite solution. but I wrote clearly on the bottom, write explicitly the final answer as x equals, y equals, z equals. That means for both of them, you're supposed to write x equals, y equals, z equals. So for B, if you wrote infinite solution and then nothing, I did not give you any points. For LU, question number 7, I was very disappointed on almost all of you because you did not verify LU. Why did I give you 1 point to verify? Not just by writing L times E equals N. No, I wanted you to really verify that it works or not, it doesn't work. Which one? If it doesn't work, means you have to go back and fix your LU. Okay. So if you did not take your LU correctly, I did not give you points. And then the multiple choice, one question which attracted my attention the most was question number 16. Which type of matrix has inverse? Almost all of you wrote square matrix. Square matrix is only one condition to have an inverse. But just because it's square matrix, it doesn't mean it's have an inverse. Okay? If the determinant is 0, even the square matrix doesn't have an inverse. So which type of matrix has an inverse? Non-singular. That's the key, non-singular. In order to have an inverse, your matrix cannot have a determinant 0. And if its determinant is not 0, we call them non-singular matrix. So if you wrote only square, I did not give you points because it is false. Square doesn't guarantee have an inverse. Non-singular guarantees that it has an inverse. And non-singular means determinant is not 0. So if the determinant is not 0, it definitely has an inverse. Okay. That's all. These are the few things I noticed in the exam. A symmetric matrix is if its transpose is same as the original matrix. A equals A transpose. That's why they're symmetric. You can write them row-wise, column-wise, doesn't matter. So remember, this Wednesday we have online class, our last online class, hopefully. Goodbye, everyone. See you Wednesday online.